Okay, we're going to look at another optimization problem, right? So want to read the problem. We'll need to draw a picture, label some things. Okay, so we have a workout room that consists of a rectangle with a semicircle on each end. So it kind of looks like a track. All right, 200-meter running track is around the outside of the room. Find the length and width of the rectangular portion so that the area of the room is maximized. So I'm going to label the two dimensions here that they asked us to find, L and W. You could use X and Y or whatever you want to describe there. Okay, so we need an objective function. The objective function is about whatever it's asking us to maximize or minimize. Objective function. All right, so we want to maximize the area of the room. So this equation here is going to describe the area of the room. Okay, so the area of the room is going to be the area that's inside this rectangle part here. That area would be length times width, plus the area that's inside these two ends here, which are both half circles. So I might have to do a little bit of mental digging and a little bit of work here to think about how to get that area equation for those circles with these two variables labeled here. I'm going to do a little scratch work over here. All right, so we know that the area of a circle is pi times radius squared. If you look at this picture here, you might notice that the radius is going to be the distance from the center to the edge. And I've got really two parts here. So this is area of a whole circle. Notice I have two half circles, which makes a whole circle. And the radius of that circle is half of this W side. So the radius is W over 2. I need to square that. All right, so if I simplify that, I square the W and square the 2, maybe put that 4 on the denominator out front here, I can rewrite that as pi over 4W squared. That's just the area of the circular part here, but that's going to help me here. So this is the area of the rectangular part, and then the area of the two half circles on each end. All right, so there's our objective function. We then want to think about the constraint. That's the restriction in the optimization problem. So for this one, the constraint, the restriction is that we have a 200-meter track around the outside. So that needs to be 200, that distance, all the way around the outside. Okay, so around the outside, I have two sides here of length L, a side down here of length L, and then a side at the top of length L. So two sides of length L. And then I have two sides of that track around the curves of the track here that would be a circumference of a circle. I have half a circumference of a circle here and another half of a circumference of a circle here. So you might remember a circumference formula for a circle, 2 pi times radius, or that's the same thing as pi times the diameter of the circle. And if we look at the picture here, you might notice the radius was W over 2, or the diameter is just that W here. So the circumference, that would be this curved part plus this curved part for this problem would be pi times W. Okay, so pi W, I almost wrote 2W. Okay, so then every time we want to think about solving our constraint for one of the variables to substitute in to the objective function to reduce the number of variables in the objective function. And in both of the last problems I looked at, I really could have done that either way. But this problem, one way is much easier than the other. If I look at this objective function, I might notice that the W is squared. If I solve this for W and substitute it in place of W, then I'm going to have to square out whatever I get. Easier in this problem would be to solve for L in my constraint, substitute in for L, and then the algebra is much easier to simplify here. All right, so if I solve my constraint for L, I'll have 200 minus pi W equals 2L, and then divide through by my 2. So I'll have 100 minus pi over 2W equals L. And the goal here was to substitute that into the objective function so that I have an objective function that has just one variable. Okay, so when I do that, substituting in for my L here, my objective function will be A equals all of this times W. I'll put the W out front. 100 minus pi over 2W plus the pi over 4W squared. And I'll probably want to go ahead and distribute through and combine some like terms here. All right, so I'll have A equals, I'll put it down here, A equals 100W. And then here I'll have a minus pi over 2W squared plus pi over 4W squared. So a minus pi over 2 plus pi over 4. It's the same thing as adding negative 1/2 plus 1/4. You'll get negative 1/4, so negative pi over 4W squared. There's my simplified version of my objective function that I'm going to use when I find my critical points. Okay, I want to think about feasible domain here. W being negative wouldn't make any sense. So I want W certainly to be greater than or equal to 0. And then I might think about a maximum possible value for W. Again, if L was 0, if I shrunk that part all the way down to 0, if L was 0, then W, the most W could be would be 200 over pi. So that's our feasible domain for this problem. Anything outside of that wouldn't make sense in the context of the problem. All right, now for the big calculus part here, critical points. Find our derivative, 100 minus, bring down the exponent, multiply pi over 4 times 2. I will get pi over 2W. Okay, I want to think about when that derivative does not exist and when the derivative is 0. We won't have any values of W for which this does not exist. So we'll go ahead and set that equal to 0 and solve for W. If I add the pi over 2W over here, I'll get that, and then multiply through by 2 over pi, and I'll get W equals 200 over pi, which we might notice was actually one of the endpoints of our feasible domain, and that's okay. That is in our feasible domain here. All right, then we want to test, and so we've talked about several different ways to test here. The one way that I haven't done in any of these videos, we'll go ahead and do here. That would be where I test for absolute extrema on a closed and bounded interval. And so to do that test, we're just going to plug our critical points and our endpoints of the interval. This is convenient here since our critical point happens to be one of the endpoints of the interval. 200 over pi into the function. And what we're looking for is the largest possible output and the smallest possible output. All right, when I plug W equals 0 into this A function, I will get 0. When I plug 200 over pi into this function, we'll do a bunch of simplifying there. I'm going to tell you what you should get once it's simplified. You should get 30,000 over pi. All right, so I'm looking for the highest. This is the minimum. And the biggest is the maximum. Right? For this problem, we want the area of the room to be maximized. All right, so this is the maximum. That's what we were actually asked for here. I'm going to go back and make sure that we answer the question. It asked us to find the length and the width of the room so that the area is maximized. All right, so our W is one of the things that we're supposed to find here. I'll just label over here on the graph. Our W was 200 over pi. Our units of distance here are meters in this problem. And then our L, I need some place to figure out what my L is. When I put 200 over pi into my equation here that relates L to W, we'll get that L equals 100 minus pi over 2 times 200 over pi, and we'll get 0. All right, so width 200 over pi meters, decimal approximation for that is about 63.66 meters. Length 0 meters. So what does that mean in terms of the room? It means that it actually is a circular room. If you want to maximize area, you end up with a circular room that you shrink this L down to 0. All right, so for that one important thing here was how I tested absolute extrema on a closed and bounded interval. The other thing is that sometimes on these optimization problems, you get that your maximum or your minimum value are actually at the ends of your domain, which sometimes means that there's some kind of strange things going on with thinking about the problem, but you have some problems in the homework that actually turn out sort of like this. So don't be surprised when those happen. We'll look at one more example.